So it turns out Taylor wasn't using the magic wand of mathematics to come up with those polynomials to approximate sine. He was actually just sticking things into this formula. But the formula is quite clever, and I've made another video in which I explain where these numbers at the front come from. It's quite a quick one to watch, so if you're interested, go and watch that, but you don't actually need to know, you just need to be able to shove everything in. So what was Taylor doing? He said f of x is sine x, we gave that to him, and we wanted something that was going to work for 0.5. 0.5 is near 0. So he obviously just took his a here to be 0. So that gave him the following formula. F of x sine x equals f of 0 plus f primed of 0 x minus 0 plus f double primed at 0 x minus 0 squared, and so on and so forth. So all he needed to do was work out what the derivatives of sine x, then the next derivative, and then the next derivative, and this isn't too hard. He knew how to do this. It's very clever. Cos x, and then the next one, fourth derivative. After a while, by the way, you don't have to write 4 little dashes, you can put a 4 in brackets, because otherwise it starts getting a bit silly. So that's back to being sine x, and then he needed to know what all these were doing at the point 0, because that's what goes into the formula. F of 0, f primed of 0, f double primed of 0, f triple primed of 0. So he had to work all these out. Sine of 0 is 0, cos of 0 is 1, and the second derivative, that would be 0 again, and you can see now why we weren't getting squared into the 4 terms, we were just getting odd ones. This would be minus 1, and then, what's this one? 4. Equals 0. Okay, so then he put this all into the equation. He was doing all this while we thought he was waving his magic wand. He was just sticking it all in the equation, and he was telling us what we wanted. So we got f of x equals f of 0, which is 0, plus f primed of 0, which is 1, over 1 factorial, x minus 0, plus second derivative 0 over 2 factorial, x minus 0 squared, plus third derivative minus 1 over 3 factorial, x minus 0 cubed, plus, etc. I've run out through. And actually I could just move it left a bit, couldn't I? Stick on another term. What was I on? The fourth derivative. So I've got 0, oh, it's 0 anyway. Never mind, 4 factorial, x minus 0 to the 4. So just putting all those ingredients into that formula and then tidying this up, it gives us, well, that first term is just going to be x. That's what we got first. Oh, I did a bad thing here. I wrote f of x. This is really bad. I need to write sine x. Excuse me. It's one of the things to remember. That left-hand side must be the function that you're approximating. Sine x equals, so that's 0, I've got that one. That one's 0 again. Now I've got minus 3 over factorial is 6. That's minus a sixth x cubed, and then that one will be 0, and then so on and so forth. So that's how you use the formula. Now this layout I want you to think of in the following way. Basically, as a sandwich. So our bread is the original formula, which is in the formula book, just the basic formula all written out. Then the ingredients of the sandwich are the ingredients of the formula, all your derivatives, and then all your derivatives evaluated at the point you're focused on. Then your bread is your formula again, but with your ingredients filled in, remembering the thing I didn't remember, which is that your left-hand side must be the actual function that you're approximating, not f of x. Let's have a go at finding the Taylor series of cos x using the sandwich approach. So here's the Taylor sandwich. Let's remind ourselves of what each of the bits of the sandwich are. So the bread at the top, that's the actual formula just copied out of the book. The ingredients in the middle, there's layers of them. You've got f of x, f primed of x, probably some more layers, some cheese, some other stuff. You've got some like pickles and things. That's the first derivative, second derivative, third derivative, layering it all up. You've also got, of course, all of those things evaluated at the point you're interested in. So f of a, f primed of a, f double primed of a, f triple primed of a, that's all your ingredients. Then the bottom of your bread is where you put the ingredients in to the Taylor series formula that you've got at the top. Remembering your left-hand side must be the function that you're actually approximating, rather than just writing f of x. This is going to make sure that everything's laid out clearly and the examiner can give you all the marks and you're less likely to make any mistakes. So let's have a go. Let's do the top of the bread now first. There we go, there's the top layer of bread, that's the formula copied out the book. Now for the ingredients. Our function, f of x, is cos x. So our first derivative is minus sine x, and our second derivative is minus cos x, and our third derivative, and that's as far as I'm going to go with this one because I ran out of room, is sine x. And then we need to know what that's doing at the point A. Now in this case, the point A, point we're interested in, is pi by 2. We're doing a Taylor series expansion of cos x, and we want it to be really, really close to cos x, near pi by 2. So we have f of pi by 2, which is cos of pi by 2, which is 0, and then we have f primed of pi by 2, which is minus sine of pi by 2. Sine of pi by 2 is 1, so that's minus 1. Second derivative, this is going to be 0 again. Third derivative is going to be 1. And now for the bottom of the bread, we're going to put all those ingredients in. F of x equals, okay, f of a, 0, plus f primed of a, minus 1, times x minus a is pi by 2, plus 1 over 2 factorial, then the second derivative at the point A is 0, so x minus pi by 2 squared is going to disappear, plus 1 over 3 factorial, 3 times 2 is 6, then we've got the third derivative at the point pi by 2, which is 1, times x minus pi by 2 cubed plus ... Tidying that up and remembering this thing about the left hand side equaling the actual function, so cos x, not f of x, we end up with minus x minus pi by 2 plus 1 over 6 x minus pi by 2 cubed. And if you want to check that, what you could do is get your graphic calculator and plot sine x, and then plot this cubic function here, and then zoom in on pi by 2 and see how accurate that approximation is. Should be pretty good. Okay, the Maclaurin expansion of e to the x, what does that mean? Who's Maclaurin? He's not Taylor. Okay, I'll introduce you to him. This is Colin Maclaurin. That is his actual name, Colin Maclaurin. And a few years after Taylor, he invented his own expansion. But do you know what it is? I don't even know how he's got away with this being called it's something to do with him, because what a Maclaurin expansion is it's a Taylor expansion, but it's centred at 0. A is 0, so the point at which it is best approximating the original function is 0. So it's a Taylor expansion. It's just a Taylor expansion. It's just a particular one. And Maclaurin somehow managed to get it named after him. Well done, Colin Maclaurin. So we'll do the Maclaurin expansion of e to the x, which is actually the Taylor expansion of e to the x, where a is 0. Here's our sandwich to remind us what to do. So we'll start off by writing down just the Taylor formula. Sorry, Maclaurin, but I'm going to call it Taylor's formula. So f of x is f of a plus f primed of a, x minus a, plus 1 over 2 factorial, f double primed of a, oh it looks like a triple prime, sorry it's not, it's a double prime, x minus a squared, plus 1 over 3 factorial, triple prime, f triple primed at the point A, x minus a cubed. Okay, so now for the ingredients, this is going to be an easy one. So we've got f of x is e to the x, f primed of x is e to the x, f double primed of x is e to the x. I probably don't need to keep doing this, do I? And so f at the point 0, because it's Maclaurin, so that means a is 0, it's just Taylor with a is 0, is 1, and that's 1, and that's 1, and this is 1 as well, and they're all going to be 1. So the bottom of the bread is the expansion, but now with all our ingredients filled in. F of x equals 1 plus 1, x minus 0, plus 1 over 2 factorial, 1, x minus 0 squared, plus 1 over 3 factorial, 1, x minus 0 cubed, plus blah blah blah, giving us a final answer of e to the x equals 1 plus x plus 1 over 2 factorial x squared plus 1 over 3 factorial x cubed plus 1 over 4 factorial x to the 4 plus etc etc etc. Pretty cool. And here's the graph so you can see what we've done. So if we just stopped at 1, that would have been an alright approximation at the point 0, but no more than that. By adding on one extra term, we get this graph, which is approximating e to the x a bit better, and then as we go further and further and further, you can see that these polynomials approximate e to the x better and better and better. So that's all there is to it. Remember your Taylor series sandwich, and then you can form your Taylor series or your Colin-Maclaurin series, which is where a is 0. And then obviously what you'll want to do is graph your polynomial and graph the original function and see how good an approximation it is, because that is always really good fun.